Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. We are discussing about single view camera geometry. In the last lecture, we discussed about the projection matrix, how to estimate the matrix and how different elements of the matrix could be related with some of the geometric entities of imaging system. In this lecture, we will consider now further the use of this projection matrix for computing the three-dimensional information of a scene. So let us first try to understand how the points are represented, what kind of three-dimensional information related to an image point is available in a projective, in a camera, in the single view camera imaging system. So we would consider the projection of a point, as we say it's a forward projection. Now while doing these forward projections, we have seen that if I once again draw the familiar diagram of the respective imaging. So this is my camera center C, and this is the principal axis, and this is say x axis. This is camera centric coordinate system. This is YC, and say this is ZC. Now you consider any particular image point, say P. So if I draw the line from camera center to P and extend it, so what I will get the respective ray, respective line, three-dimensional line passing through the camera and passing through the image point. So all the point lying in this line, its scene point lying in this line is mapped to this particular point P. Now we consider, say, so what is the farthest point that could be mapped here? And farthest point is here actually point at infinity, but there is a direction associated with it. So if I consider, say, this ray has a direction D, then we know that at infinity, towards infinity, the point which is lying at this infinity, that can be represented by D0 in the homogeneous coordinate system. You note that this is a scale dimension, additional dimension, and D is a direction ratio. D is the direction which is expressed in terms of a vector of direction ratios, and which is a 3×1 vector. So this becomes a 4×1 column vector in our representation. So we call that this is a point which is at infinity along this ray. So for this point also, this projection still it is projected on P. So if I consider this imaging system has the projection matrix P, then we say this is P, then P, and when I multiply the point D0 with P, that is a transformation, then actually I will get this point. Since I am denoting it by P, let me also denote in this point. So it's an respective point in the image plane, and it is represented in a 2D projective space. And the point at infinity is, there is a term is also which is called the vanishing points, or the ideal points in a three-dimensional projective space, and the plane at infinity is a concept is same as the plane at line which is extended in a three-dimensional projective space. So if I say this is a three-dimensional projective space, then the plane at infinity, which I will denote by pi infinity, which is actually the extension. So, if you remember that line at infinity in the two-dimensional projective space, it was represented by 0, 0, 1 in a two-dimensional projective space. Similarly, plane at infinity in three-dimensional projective space also can be represented by 0, 0, 0, 1. So, if I take any ideal point or any vanishing point in the form of say D0, where D could be any arbitrary direction which is a 3 cross 1 column vector, then the plane at infinity. So, if I take the point containment, we will find that this is equal to 0. So, any ideal point lies at plane at infinity, like any ideal point into the projective space lying at line at infinity. So this is one kind of concept that how actually you can express the projection ray and a point at infinity D0. So, if this is the thing, then what we can say that we can consider a particular configuration, as I was saying. So, if this point is x, let me use the usual notation what I am following here. So, consider this is a point x and this is a point sin point x, which is lying, whose coordinate is t0. So, we can say that the projection of this point could be computed as the multiplication of the projection matrix P, as we have shown here, so which is again represented in the familiar submatrix form arrangement. So, this M is 3 cross 3 submatrix. So, this is what is P projection matrix, and then it would be simply M into D. So, if I am given the projection matrix and given this projection ray X, given the image point X, then the D could be computed as M inverse X. So, that is the interpretation. That is a three-dimensional scene interpretations for an image point. If I know the respective projection matrix, I can relate that point with the line of projection, whose direction ratio I can get. So, this is a direction ratio, and as you know that to define a straight line, you require direction and a point in the three-dimensional space, and which is already given by the camera center. So, we note this also fact that the respective projection of any point lying at plane at infinity, which is denoted by the respective direction, this is only affected by the M, parameter M, which includes the rotation matrix, but this is not affected by the column vector P4, which actually contains the translation vector. So, we consider that the projection of a point at infinity at any direction, it remains the same even if your reference frame translates, I mean without any rotation. Say this can be explained by our visual observation. Suppose because our eye is also like a camera where there is a lens, and if we have a motion, say we are walking and we are looking at the moon in the horizon, and by keeping the direction, you will also see the moon is also walking as if with you, which means in your image, as an image point in your retina, the point of intersection from that direction is not changing. So that can be explained, that phenomena can be explained mathematically by these relationships. Now, these relationships can be expressed in terms of back projections, what I was just referring at, which means that if I have the image point x and expressed in the homogeneous coordinate system, then if I do the M inverse x, that will give me this direction, and that is the this point is this one D0 or M inverse x0. So you can also see that simple algebraic matrix algebra, that if I perform this multiplication, then actually I am getting back the x, because m into m inverse x is x and P4 into 0 is 0, so it is giving me x. So this is the scenario, as I was mentioning, that you have the camera center on that line, and you have a point at infinity along this direction, which is m inverse x direction. So this is the direction, and this is a point at infinity. So the parametric representation of this straight line in the three-dimensional coordinate system can be expressed in this form. So mu is the parameter. So mu into d plus c. This is one representation. You can see that mu into m inverse x 0 plus c tilde 1, and then the c tilde, that is c tilde is the three-dimensional coordinate of the camera center. It is a non-homogeneous coordinate, so it is minus m inverse P4. And finally, in the composite form, we can write these two. These two can be clubbed together to make it m inverse into mu x minus P4. So this is a simple relation. This is the relation of the straight line. I mean, this gives you the coordinate of the points lying on this line and defining the line. So if you vary mu, so say vary mu from say minus infinity to infinity, you will get all sorts of points. So when mu is positive, so you will get point in these directions. So when mu is negative, you will get point in these directions. So another thing also from as a following of this discussion, we can find out that we can define the depth of a point. So what is the depth of a point? Suppose this is the point, which is also a three-dimensional scene point. So the depth is the distance of this point along the principal axis. So if I take the perpendicular projection of the vector forming actually perpendicular projection of x tilde, or if I take the take the projection of the vector on the principal axis, that would give you the respective depth information. So depth can be computed as you see that this direction is given by the MR3 unit vector. MR3 is the 3 elements of the third row vector, first 3 elements of the third row vector. That gives the direction ratio of the normal of the principal plane and also direction ratio of the principal axis. Now, the computation of the camera center we have already seen, and there we have seen that we can compute using the inversion of m. So, just to write once again that c tilde, this quantity, which is the camera center's three-dimensional coordinate in the non-homogeneous coordinate system, is equal to minus m inverse P4. So you require an inversion, but no, there is a way by which this inversion also can be avoided. If I apply simple Cramer's rule for solving a set of linear equations. So the set of linear equations is given by this thing from where actually we are getting c tilde. Instead of that, we can write it m c tilde equal to minus P4. So now you see that your unknown is c tilde, which has the 3 coordinates. Say we say those coordinates are given by xc, yc, zc. Say c tilde is given by xc, yc, zc. So if I write this equation, we will write it as m can be written in the form of P1, P2, P3. It has been shown here itself, and then the equation would be P1, P2, P3, xc, yc, zc. So that is equal to minus P4. So using Cramer's rule, we know that this can be expressed as ratio of 2 determinants, where the columns are respective columns are replaced by the column at the right hand side. So that is what for xc you replace the first column, and this determinant is always the same. Then for yc you replace the second column, and then ZC you replace the third column. And this is how we can compute easily the coordinates of the center, and you do not require inversion directly. The another thing we would like to discuss here, that how actually you can estimate the camera parameters if I give you the projection matrix. As you understand that projection elements of the projection matrix, they contain the information related to the camera parameters, such as those extrinsic and intrinsic parameters. So from the composition of camera parameters, we know that in various ways this encoding is expressed. For example, if I consider this representation, we can see that there is a factor of camera center here itself. If I consider this representation, then we can see the rotation matrix is already there, and the calibration matrix, camera calibration matrix also can be obtained. So in this way, various way you can do it. So the first thing what you can do, that if you know since you know the M part and you know M equal to KR, so there you can do the RQ decomposition, where R is an orthogonal matrix and Q is a upper triangular matrix. So this decomposition is possible. So here actually in this case K is an upper triangular and R is an orthogonal matrix, but you can have also the RQ decompositions where you can perform this. So use these constraints, and there is an algorithm by which you can get those factors. Now these are not unique answers, unique decomposition, but most likely they are one possible answer, and they will give you some indications, and many cases they provide you realistic, plausible values for those parameters. And then once you know this calibration matrix with these two factors, by matrix factorization K and R, you can and also you can obtain the camera center by using M and minus P. We have already seen that, minus M inverse P for camera center. And from R you can get the orientation parameter, and from K you get the elements of calibration matrix, and this can give you the translation parameter. So in this way you can get the parameters related to imaging configurations that from the matrix, the projection matrix itself. So now I will provide one example by solving an exercise that how all these things could be computationally obtained from a projection matrix. So take this example. So you have a projection matrix, and you can see that these are the elements, and these are the column vectors. You can see these are the column vectors. There are 4 column vectors. So first you compute the camera center. So you know that camera center can be computed if this forms a M. So take once again that formula of minus M inverse of P4. That would give you the camera center. Or you can use Cramer's rule. Then the vanishing point of x-axis, and vanishing point of x-axis is this column vector P1. That is the column vector. Image point of the origin. So image point of the origin, we know that this 4th column vector is image point of the origin. Or vanishing point of the line with the direction cosines 2:3:4. So we know this can be represented as M into D, where D is given by 2, 3, 4. Okay, D is given by this, and M is given by this 3×3 submatrix. Let us consider another example. Say you have a projection matrix, and this is the projection matrix. Now, if I give you an image point in R square, which means it is expressed in the non-homogeneous coordinate system, we need to compute its corresponding scene point if it is known that the point is at a distance 40, which means that through back projection I can form the ray through which intersects image point at 2, 7 and passing through the camera center. So that would give me the equation of the line segment or straight line, and in the parametric form I will use the distance. The parameter is basically the interpretation of the parameter can be done with respect to distance. So this is what we are going to do. So if we have a direction ratio LMN, then you can express this in the parametric form. You can express this equation as in this. This is the parametric expression, parametric form. So this is the direction ratio. So you take the unit vector in this ratio, and mu is the distance. So the any point can be expressed as the C tilde, this source point or the end point, plus distance into the corresponding direction, corresponding unit vector of the direction. So that is what we are doing here. So we compute this direction ratio using M inverse D. If you remember, that image point is 271. So M inverse of that will give you the corresponding direction. And if I apply this, then we will find out that point. Then the other using that projection matrix, we would like to compute the principal plane of the imaging system. So once again, if you remember that with our analysis, we have shown that principal plane is expressed by 1 minus 581, which means these are the coefficients A, B, C, D, which gives you a plane x minus 5y plus 8z plus d equals 0. So let us now consider some other cases of imaging geometry. One of the special cases is that when cameras are at infinity, because we have seen that in this case you are not really getting a finite camera center, and the rays are not converging as in the Euclidean sense. So what happens that in such a case, camera center lies at the plane at infinity, and there are two situations. One is that your projection matrix, the respective projection matrix, the last row could be 0, 0, 1, and this is a case of affine transformation when M would be singular. In all the cases, M is singular and otherwise non-affine. So we will be basically considering affine case where the last row is 0, 0, 0, 1. If you remember, in the homography also, we considered the 3 cross 3 projection projective transformation matrix becomes affine projective transformation matrix when the last row is 0, 0, 1. So it is a similar kind of structure, as you can see. So for an affine camera, so this camera is known as affine camera. So if I write the camera in terms of this, so we can write it as, say, this is the first row, which would be some value, this will be some value, there are 4, and but the last row will be always in this form. So if I write the, say, A, B, C, D, then say E, F, G, H, and then. So we can see also that in this kind of projection matrix, so if I write PA just to denote it is affine. So this representation is since the scale is already determined by 1, already it is specified by 1. So all these elements with this representation is unique, because if I multiply with k, then all this would be multiplied by k. But moment we keep it 1, so all these elements are already uniquely represented. So that is the advantage of this representation. So once we start with this fixed third row representation of an affine projection matrix, there are certain advantages that we will see later on. So these are certain properties, as I mentioned. Principal plane is the plane at infinity, which means the plane where your x-axis and y-axis and the camera center, which contains this plane, this principal plane will be at a very large distance. So all the rays are trying to intersect at that point, which is an ideal point. So it has to be a plane at infinity. Your camera center is a plane at infinity. That's why camera center is an ideal point. Camera center lies in plane at infinity. you note that this is a 3D projective space on which we are discussing about this plane at infinity, camera center, the point in this case. The other thing is that in this case, the parallel lines still remain parallel after projection, because when you are having parallel lines, now the point of intersection of that parallel line in the three-dimensional space itself, in the projective space itself, that would be at infinity, which means it is a point at plane at infinity. So when you project that point at plane at infinity, even in the image plane, that would be also a point which is which should be an ideal point. That means which should be a point at infinity. So this is the form of affine projections matrix that we will be considering. I was just showing with those with those notations of A, B, C, D. Instead of that, let me use the standard matrix element notation. So this is the element of the submatrix M, and this is this translation vector. Only we are considering here 2 cross 1 representation of the translation vector, and as you see that this becomes the a representation which is a fixed for the third row. So using this representation, what you can see, even the non-homogeneous representation of the points, three-dimensional points and two-dimensional image point, they have a linear relationships. They have not linear, they have an affine relationships, but they could be easily expressed. So these equations this equality is a hard equality with respect to the observed scene point and the image point. So this makes the problem of estimation of affine transformation, affine projection matrix is simpler. First thing, there are less number of parameters in them or elements. So you have only 8. So the first row 4, second row 4, and third row is already given. So since there are only 8 parameters and 8 independent parameters, and you have a point correspondence which will give you once again 2 independent equations. So this is the equations, and this could be also represented in this form. As you can see, I have used a 2 cross 3 matrix. So since there are affine projection matrices 8 degrees of freedom, and we require minimum 4 point correspondences to solve this problem. But naturally, for a robust computation, you can have more number of points, and so we will see that computation bit later. First, let me talk about this camera center. Now, since it's a singular, this M is singular, because if I note the structure of M, you will find that it is M11, M12, M13, then M21, M22, M23, and the last row is 0, 0. So this is that 3 cross 3 submatrix. So naturally the determinant is 0, and which is singular. So what happens that the camera center is given by the respective right null vector of M. So the camera center is at the direction of parallel rays. So in the case of affine, instead of converging rays at the center of projections, we have rather parallel rays which is intersecting the image plane. So for any object or any scene point x, you take a parallel ray along the direction, and where it intersects, that is the image point. So this is the interpretation. So the camera center is the intersecting point, or rather I should say camera center is lying at the so this direction represents the point. So which is the point at infinity along this direction. Once again, this is that ideal point, and which is given by the direction and the 0. So this is that 4 cross 1 vector in the homogeneous coordinate representation, which will give you the camera center for an affine projection matrix. So how this D could be computed? So since D is a 0 vector of M, we have to solve this problem, MD. And for that, using the same mechanism, so this is what you need to solve, M2 cross 3D equal 0. So use this. So what we will do usually, that we may consider the first two element of D, say D1 and D2, and we may consider say D3 equal to 1. Then this matrix says, let me write it as M11, M12, M21, M22, and say in the same way M13 and M23. So let me write this submatrix as say M2 cross 2, and let me write this one as say M2 cross 1. Okay. So if this is 0, and let me write this vector as say D2 cross 1, because 1 is already determined. So if I expand this equation, it would be M2 cross 2 D2 cross 1 plus M2 cross 1 equal to 0, which means D2 cross 1 can be obtained as inverse of M2 cross 2 into M2 cross 1. Now, this is one case, but it could be there is a degenerate case. Suppose this value is also 0, then actually this is not applicable. So the computation of null vector could be in a different form. You have to make singular value decompositions, and from there also you can get this null vector. So these are the certain things we should note. First thing is that image of the world origin is at T, because the world origin is given by 0, 0, 0, 1, and the affine matrix, if I write the affine matrix, you can see that I will be writing it as say M2 cross 3. This is a 0 vector, which is a basically 1 cross 3 0 vector. This is T, which is 2 cross 1, and this is 1. So if I perform this computation, then this M2 cross 3 and so this is 2 cross 3, right. So this one and this one, that would be equal to 0 plus T2 cross 1. So which is that T itself. So that is why image of the origin is T. Then the principal plane for projection matrix PA is the plane at infinity. We have already discussed that why it should be, because because all the points which are, because your camera center is also lying at plane at infinity. Parallel world lines remain parallel in image, which means that in the 3D coordinate system, which is the world coordinate system, whichever line is parallel, and if I take the respective images, as you understand that in this imaging, it is the direction which is important. It is not in the affine cases. So this should be one image, for example. Similarly, if I take the other image, if I extend it, then the other image. So these two lines, image lines, also should be parallel. So that is the idea here. And then M2 cross 3 should be of rank 2 to ensure PA to be of rank 3. So this is also another constraint we have to consider. Now the estimation of affine camera, as I was discussing. Now since this case is simpler, because you can write this set of equations in this form only. So you note that this R1 is the respective column vector of this row, and R2 is the respective column vector of this row. Then actually the coordinate xi is basically, as you can see, we can write it as this equation, xi into R1, that is giving you xi. Xi also should be transpose. This is something I have missed. So xi transpose R1 should be equal to xi, and xi transpose R2 should be equal to yi. These are the two equations directly coming from here itself. You can find out from there. So this one gives it to, so from one image point correspondences, like the way we have estimated projection camera matrix, for affine projection camera matrix also you get 2 equations, and since you require only 4, we require 8 such equations. But as you go on for more number of points, you can make it like this. Now in this case, you note that this is not a set of homogeneous equations, this is a set of non-homogeneous equations. So you can directly apply the least square error methods for solving this problem, which means this is a pseudo inverse of this one. So once again, let me just explain that how this pseudo inverse can be related using simple matrix algebra. So if I write in this way, then I will multiply A transpose in this side. Now you see that A transpose A, suppose this should be this is a square matrix, and if it is invertible, most likely it will be invertible, then we will be considering A transpose A inverse A transpose B. So that is the solution, and this is the pseudo inverse that we are considering. So we discussed about this affine camera matrix, and let us now consider imaging of some of the special cases of geometric configuration. Say you would like to image a plane. Now when you image a plane, then what happens that we can see, because the scene point is very much restricted on the planar configuration, and as we know that the transformation in that case, suppose I have a plane here and I am imaging this plane, and this is my image plane. So if I have a point here, for example, now this is my image point and this is a scene point. Now this is an one-to-one correspondence, because my plane, this ray intersects the plane only at this point. This projection ray intersects the image plane at this point. So these are uniquely, uniquely mapped, one-to-one mapping. That is one thing. Second thing, as you see, because of that, it is invertible. So if I know x, I can get x. If I know x, this scene point I can know. Invertible. And the other thing is that if I consider a straight line, even the projection or this mapping, it would be also a straight line. And since it's a two-dimensional plane, I can consider the coordinate system. So if I can choose some coordinate representation of this plane to make it a projective space. And similarly, the image plane, it has also an implicit, we can make it a projective space. So this is a mapping from one projective space to another projective space, which means it's a projective transformation. So the imaging of a plane itself means there is a projective transformation associated with it. That means there is a homography between the mapping of planar points to its image points. Now let us consider the other case when we are projecting a line. Say this is a line, it's a three-dimensional line, and once again, this is the image plane, and say this is the center, camera center. So if I take the projection, then I will get the projection also as a line. So this L is giving this line. Now if we consider, as you understand, this line and camera center, it makes a plane. So all these entities, they lie on a plane. They lie on a plane. Now can we get the equation of this plane given this camera C, given the projection matrix of this imaging system is P? So let us say that if I consider the point containment relation, suppose x is lying on L, I can write this x transpose L equals 0, that is the point containment relation. And again, since x is the image of x, so we can have the relationships x equals Px with this projection matrix. So I am just replacing x by this relationship. So Px transpose L, small l is 0, and using the matrix algebra, x transpose P transpose L equals 0. So what you see here, this quantity is a 4 cross 1 vector. because P transpose is a 4 cross 3 matrix, and L, which is a line specification in the projective space itself. As you know that line can be represented by element in the projective space, it is 3 cross 1. So, which gives you a matrix 4 cross 1. Now, this is an entity which is representing a plane. So, I can say this is what is basically pi, plane. So, the equation of the plane is given by P transpose L, pi equals P transpose L. So, this is the interpretations from this. Now, let us consider another scenario when we would like to see the respective transformation of the images of the two images when the camera center is fixed and the image planes are moving. So, one is that fixed camera center and moving image plane, and we have shown here how the image planes are moving. Say, since image planes are going through this kind of thing, so they are related with, so they, each one of them will have two projection matrix. As I mentioned, one camera center is fixed, but this camera center and this image plane and camera center and this image plane, they give you, say this is P2 and say this is P1, two different projection matrix, and there are parameters associated with them. So, this P2 is represented by this. You see this, since the C is fixed, this component will be fixed for P1 also, and their parameters are corresponding calibration matrix and rotation matrix are denoted in this form. So, now since you take the same scene point and you consider the corresponding two image points, and we know actually it is forming a projective transformation between these two image spaces, because the if I take a line, it would be also, line would be also transformed to line. It's a one-to-one transformation, as we can see, and these two are planes which can be expressed in terms of which are represented, which are also projective spaces, if I consider this center. P2 and P1, they are related by this, and this is coming from these relationships. Keep this portion the same for both. So, you can take these things here as K2R2 inverse P2, similarly K1R1 inverse P1, and then equate them. From there you will get this relationship. And then as I was showing you that X2 and X1 can be related from this relationship. So, this is how the homography is defined between them and how homography is explained in terms of respective camera parameters. Now, when we consider a simple zooming case, so when there is a simple zooming, which means your rotation is there is no rotation, it is basically an identity matrix. But your camera plane is image plane is shifted by a factor, the distance from the center is varying, and suppose there is a ratio by which this is shifted. So say this is f2, this distance say is f2, and say this distance is f1. So, it is a parallel image plane. Image planes are parallel, they are moving because there is no rotation of the corresponding image axis. So, in this case, you can show, because rotation matrix is equal to R2 equal to I and R1 equal to also I, and camera center remains same. So, from previous relationship itself, we can see that the corresponding homography become more simplified as K2 K inverse. The other factor which I would like to point out here, that you can compute the vanishing, we have already discussed about vanishing point, and there we have seen, let us try to understand that vanishing point concept. Say you have a line, and as I mentioned that it's a this is the case of one-dimensional projection. So, the space is a one-dimensional, which is a line, and consider your image, you are projecting it also in a line, and there is a center of projection C. So, if I draw any point, take the projection of a point on the line, this is a projection. Similarly, take the projection from this point. Now, this is the projection point. But if you go like this, as you are approaching towards infinity, finally you see that they are approaching towards vanishing line, which is nothing but the line parallel to this line, and this parallel line where it intersects the image line, that is the vanishing point. Now, this is the interpretation is one dimension. Now, same interpretations can be extended to two dimension, in our usual image configuration. Here you have the center of projection, this is the image plane. So, if I consider a line which is parallel to it and where it is intersecting, now this vanishing point, say this is the point Q of image point of Q in this line, this is the point R, and this is the point V where this line is parallel to this line. So, naturally these two lines are not intersecting. It is intersecting at infinity, which is at the projection of the point at infinity along this direction, and that is what is the vanishing point. So, given this direction, once again we have seen that this is the expression earlier also we discussed. We have taken the simple canonical projection matrix formation using the calibration camera. And once again, vanishing points are independent of camera position if it is not rotated. So, with rotation R, it becomes KRD, because if I have the rotation, then this is R and say this is 0 in this canonical form, D0, so it would be KRD. So, that is what you will get here. So, if we know the corresponding vanishing points of a camera, and if we know the calibration matrix K, then you can compute the rotation between these two views. So, this is the idea. So, because this V prime is KRT, and from this you can also compute the rotation between these two. Like vanishing point, the vanishing line also can be explained with this camera projection matrix, this imaging configuration. In this case, we consider all the lines, say they are in a plane, the parallel lines, they lie on this plane. So, there are certain directions for which only you will find they are orthogonal to this normal, and only for those directions you will get you can define their vanishing line. So, for all of them they will get a vanishing point in the image plane, and it can be shown that all of them lie on a image plane on a line, because the point of intersection of these parallel lines, as we know, they are also ideal points with respect to a projective space defined on this plane. So, which means even the vanishing points also, they would be collinear, because these points are basically lying at the line at infinity of the respective projective space. So, this can be geometrically interpreted in this way, that you consider a plane parallel to this plane, which means which has the same normal and which is passing through the center. So, the intersection of this plane and the image plane, they give you the respective vanishing line. So, this is what is your vanishing line on this plane. So, each plane will have a vanishing lines, and with this, if I know the vanishing line, then from there itself we can also compute you can see that from there you can compute the plane P transpose L, and you can get the respective normal for which for the plane for which it is a vanishing line. So, let me summarize this whatever we discussed under this topic. First thing is that pinhole camera, it provides the projection matrix which maps a 3D point to an image point, and a projection matrix, it's in the form of 3x4 matrix, its dimension. Then there are 11 degrees of freedom. There are 5 intrinsic parameters and 6 extrinsic parameters that we discussed, by which can account those degrees of freedom. And for estimating a projection matrix, in general, you require 6-point correspondences. But when you talk about a special case of projection matrix where the last row is in the form of 0, 0, 0, 1, say last row is, then we have only 8 unknowns. And that matrix is also called affine projection matrix. So this is the formulation. Its degrees of freedom is 8, as I mentioned, and you require only minimum 4-point correspondences for its estimation. Then there are several geometric information that is encoded in a projection matrix we have seen. For example, you can take the columns or rows of the projection matrix, and each one has its own interpretations. So camera center is given by minus M inverse P4 from this configuration. Then for affine projection, of course, you have to take right 0 of M, that is the direction, and vanishing points of coordinate axis are P1, P2, P3 respectively, and also the image point of the origin of the world coordinate space is P4. Then there are certain special planes which are denoted by these row vectors. For example, R3, it is the principal plane, and the direction of the optical axis, or which is the normal to the principal plane, naturally is given by these 3 elements R31, R32, R33. That means first 3 elements of this R3 vector. Then the principal point also can be computed as a vanishing point of that direction, which is given by this. Then the plane formed with y-axis of image coordinate is R1 transpose x equals 0, and x-axis is R2 transpose x equals 0. Some of the geometric derivatives from projection matrix, like projection ray formed at image point x, this could be, its direction ratio is M inverse x, and a point on the ray is the camera center, which is given by minus M inverse P4. And the plane formed with a line L in the image plane with the camera center is P transpose L, that we have seen. And its vanishing point of a line with direction D is given as M into D. So with this, let me conclude this topic here, and we'll discuss about in subsequent topics about particularly binocular view or stereo views of stereo geometry of camera of imaging systems, stereo imaging system. So thank you very much for your patience and listening.